Hi everybody. So the next chapter we're going to look at is chapter 13, and this is about comparing three or more means. So in the last chapter we looked at comparing in section 12.2, right? We kind of looked at comparing two or more proportions. So in this chapter we'll look at comparing two or more means, and we'll do some more in-depth analysis in this chapter as well. So the first section we're going to look at then is 13.1, and this is called one-way analysis of variance, or ANOVA for short. And so these are some of the things we'll look at in this section. We'll look at verifying the requirements to perform a one-way ANOVA, test a hypothesis regarding three or more means using a one-way ANOVA. So analysis of variance is sometimes called ANOVA for short. It's an inferential method used to test the equality of three or more means for different populations. I guess one way you could do this is if you use the techniques back from chapter 11. You could sort of conduct, if you think about it, you could conduct three separate hypothesis tests. But the disadvantage of this is that the probability of making a type 1 error will be much higher than alpha, so it's probably not a good way to do that. So what we'll look at is this other ANOVA method. So the first thing we need to do is talk about what requirements have to be satisfied in order to perform a one-way ANOVA. So the following conditions here: that there must be k simple random samples, one from each of the k populations or randomized experiment with k treatments. The k samples are independent of each other, that is, the subjects in one group cannot be related in any way to subjects in a second group. The populations should be normally distributed, and the populations must have the same variance, that is, each treatment group has the population variance sigma squared. So again, here's the hypothesis test then. So the hypothesis test is that the three means are the same, or at least one population mean is different from the others. Now we won't be able to tell in this section which one of the means is different from the other ones, but we will be able to kind of tell that in the subsequent sections 13.2. But we will be able to at least detect whether one of the means is different from one of the others. So as far as testing using ANOVA, the methods of a one-way ANOVA are robust. So small departures from normality will not significantly affect the results of the procedure. In addition, the requirement of equal population variances does not need to be strictly adhered to, especially if the sample size for each treatment group is the same. Therefore, it is worthwhile to design an experiment in which the sample sizes from each of the populations are roughly equal. So as far as verifying the requirements of equal population variance, the one-way ANOVA procedure may be used if the largest sample standard deviation is no more than twice the smallest sample standard deviation. Again, a lot of these requirements you won't have to worry about in practice on the homework, but in real life when you're conducting an experiment, you'll have to do that more likely. So let's look at an example here. So let's look at some data here of the weights in grams of pennies minted at a Denver mint in 1990, 1995, and 2000. Verify that the requirements in order to perform a one-way ANOVA are satisfied. So here are the weights. So let's talk about the requirements here. So the three samples are simple random samples. The samples were obtained independently, right? The weight of one year pennies shouldn't really affect the date or the weight of the other pennies from the other years. And then again, you'd have to construct a normal probability plot for the 3 years. But again, those should all be roughly linear if you want to look at the probability plots. Again, I'm not going to have you construct these, so you don't really have to worry about that. But if you do construct the normal probability plots, you'll see that the normality is satisfied. Again, in a lot of problems, you'll be given this data, or you can just assume that the assumptions are automatically satisfied. So let's look at the solution. So the sample standard deviations computed from each of the sample, we're going to just use a computer program like Minitab or something, will be shown on the next slide here. And the largest standard deviation is not more than twice the smallest standard deviation, so the requirement of equal population variance is considered to be satisfied. So again, you'll notice that here's the standard deviation from each one, right? And you can see that it does satisfy the conditions. So let's continue on to objective 2 on testing a hypothesis regarding 3 or more means using a one-way ANOVA. So we've talked about the conditions. So the basic idea of one-way ANOVA is to determine if the sample data could come from the populations with the same mean, or suggest that at least one sample comes from a population whose mean is different from the others. So to make this decision, we compare the variability among the sample means to sort of the variability within each sample. We call the variability among the sample means the between sample variability, and the variability of each sample within sample variability. If the between sample variability is large relative to the within sample variability, we have evidence to suggest that the samples come from populations with different means. And the calculations here can get to be a little cumbersome here. So a lot of times, like on the exam, I might just give you guys the output from Minitab or something like that. But so the test statistic in this case will be the between sample variability divided by the within sample variability, and so we're going to basically call this the mean square due to treatments. We'll abbreviate that with MST, and the bottom we'll call the mean square due to error. We'll call that MSE. So step 1 is to compute the sample mean of all combined data by adding up all observations and dividing the number of observations. Call this X bar, and then find the sample mean for each sample, and let X1 bar represent the sample mean for sample 1, X2 bar represent the sample mean for sample 2, etc. Right? And then find the sample variance for each sample. And I should mention too that this procedure is outlined on page 627 in your book, in that purple box. And then compute the sum of the squares due to treatments, the SST, and then the sum of the squares due to error, which we'll call SSE, and then divide each sum of the squares by its corresponding degrees of freedom. So you would divide the SST by k minus 1 and SSE by n minus k respectively, and that will give you the MST and the MSE. If you divide this by that, you'll get the MST, and you divide the SSE by n minus k, you'll get the MSE, and that will allow you to compute the test statistics. So there can be a lot of computations here, especially if you're doing this by hand. So I'll probably, on the exam, I'll work out at least some of the computations for you, if not all of them. Let's actually go through computing the F statistic in this case. So compute the overall mean. So take all the data in your sample and compute the mean of that. So we had a total of 33 pennies. And then find the sample variance for each treatment, right, for each year in this case. So again, I'm not going to work out that exactly, but here's the mean for each one. And then you'll have to calculate the standard deviation from that. So again, you can see this is a lot of work if you're going to do this by hand. And then compute the sum of the squares due to treatment, the SST, and the sum of squares due to error. So again, that's given by that. And again, these formulas are given on page 626 in your book. And then finally, divide the SST by k minus 1 to get this, and to compute the MSE, divide the SSE by n minus k, the total number of samples divided by the number of categories you have. So you had 3 years for each one of the pennies, and that will give you that number. And then finally divide these two last numbers. So divide 0.005 by 0.004, and that will give you, in this case, a value of 1.25. And so if you look at the ANOVA table here, you can sort of summarize the data here, and the F statistic is given here. And a lot of times in like a mini tab output or something, you'll get that it's put in a table of this form. So again, I may just give you sort of the output, or have compute some of these values and expect you to fill in the rest of the table here. And so basically then that should basically be what you're expected to do in this case, is to calculate those sorts of things. So so again, this is pretty computationally intensive if you're going to do this by hand. So a lot of the problems, I will at least do some of the computations for you, or I may just give you an output like this and have you read the output. So but try some of the problems by hand, at least a couple. Again, some of these you can maybe do in a spreadsheet, and things like that. So and there is also, if you look on page 637, there is a technology step-by-step that will show you how to do this, using a TI-83 or 84 Minitab, Excel, and StatCrunch. So again, that would be another way to do this, because people don't really do this by hand now that we have sort of modern computers. But if you did want to program a computer to do these, to do this ANOVA test, you would have to know the formulas and be able to program the formulas into the computer. So, all right. So hopefully that should give you at least some idea of what to do with that section. So I know we are getting into some more computationally intensive stuff here. So if you do have problems, just let me know. And just to let you know, this will probably be the last section I'm going to test you on in the exam. I do want you guys to do the homework from 13.2 and 13.3, just because it basically extends this test to, so all the analysis of variance test tells you is whether one of the means are different. It doesn't tell you which one is different from the other ones, or if they're all different, and that's what's talked about in the next couple sections. So, and then maybe just to continue on here, and then the decision. So the decision rule in a one-way ANOVA test is if the p-value is less than the level of significance, reject the null hypothesis, right? And here we are calculating an F statistic here. So, and then a lot of times the p-value will be given to you in the table as well. So again, that's something I'll either give you or something like that. So, all right. Well, I hope that makes sense. If you guys have any questions or anything, let me know. The next thing we'll look at here is 13.2 on post hoc tests on one-way analysis of variance. In other words, after you've done the test, what post hoc just means after the test, what can you do after you perform the analysis of variance test? In other words, is there a way to determine which one of the means is different from the others, or are all three different? But like I said, I'm probably only going to test you up through 13.1, so the exam will pretty much cover chapters 1 through 12, and then section 13.1. And I did assign, like I did assign 13.2 and 13.3, and also 14.1, because that kind of goes back to chapter 4. But I don't think I'm going to test you guys on that stuff on the actual final exam. So just to let you know, I'll probably be sending out an email about that in a couple of days anyway. But all right, so if you guys have questions or problems, just let me know.